Hello and welcome to the Lab4 introductory video. In this lab you're going to design and implement and test a number of counters. I hope you enjoy it. I'm going to discuss the following topics in this video. I'm going to briefly go over the requirements of the lab, then provide a number of demonstrations of the aspects of the lab that you will need to work on in order to fulfill the requirements of the lab. And then I'll finish off by explaining what help is available and how you should go about the submission. All right, as with all the labs that you're going to be doing in this course, it's really important to prepare before you start. The main things to do are to read the Lab4 exercise sheet and to watch the Lab4 introductory video. Then you can work on the individual parts of the lab that are to be submitted. For this lab, you're going to need to submit your work on parts 1, 2, and 4. You're going to be also asked a number of questions on the work that you did in parts 1 and 2. So please answer those questions, provide your answers together with the paper design, the block diagram that you're going to create for part 4. You need to submit your paperwork, the part 4 design, as well as the answers to the questions from parts 1 and 2, as well as your archives for parts 1, 2, and 4. Obviously, we're also going to be ongoingly interested that you practice good coding style. So just make sure that everything's nicely aligned, easy to read, that you're using behavioral code correctly, correctly decomposing components and instantiating them. Right, so the first part of the lab asks you to implement an 8-bit synchronous counter based on the 4-bit design that you see at the bottom of this page. You're going to be implementing a structural counter, having designed a toggle flip-flop, described a toggle flip-flop. That toggle flip-flop, that can be described behaviorally, but once you've described that toggle flip-flop, you need to instantiate it 8 times with the AND chain as you see in the diagram below, so that it's a synchronous counter with an asynchronous reset. In the lab, after you've described it, you're going to confirm that the structure is correct of the counter. I'll show you how that's done in a moment. And then you're actually going to determine what the critical path length for this counter is, and therefore what the maximum frequency is that you could operate this counter at. That's a slightly involved procedure to find out what the critical path length is, and it's founded on firstly determining what the worst negative slack of the circuit is, or which path has the minimum slack available on it beyond the clock period that's available. Finally, in terms of assessing the design, I'd like you to find out how many lookup tables, flip-flops, and I/O pins are used, i.e. what the utilization of this design is. Because I want you to compare the results that you get for part 1 with the results that you get for part 2. So let's have a look at how all of these things are done within Vivado. Once you've completed coding part 1 for Lab 4, you could have a look at the structure that's been generated for your 8-bit counter by having a look at the RTL analysis schematic. This brings up a panel with a block representation of your design, and as you can see here we have a chain of AND gates and a number of flip-flops, 8. We can dive into this design a little, have a look at it a bit more closely. Note that there's a clock and an enable input and a clear input here as well. Having a look at the least significant bit of our counter is actually this flip-flop here. If we dive into that, we can see that this is a D-type flip-flop with an asynchronous clear that comes from the N clear signal, and the toggle flip-flop is implemented using an inverter on the output, which is enabled via the chip enable signal on the flip-flop. Apart from having a look at the schematic, I'd like you to have a look at some of the performance characteristics of this structural counter. In order to do this, we're going to have to actually apply a clock constraint to get some idea of what the critical path length is. You do that by editing the timing constraints on the implementation. That brings up an input page of timing constraints. You can ignore this violation. That's merely because we're using a manually controlled clock. This timing constraints panel allows us to create a clock constraint. So double clicking on that allows us to create a constraint which we'll call clock. And we want to pick the signal to apply that to. This will list all signals. That's the clock signal we want to apply this to. Unfortunately, the GUI is not particularly clever. I need to adjust it to get the bottom button. And now we have our clock constraint associated with the clock. We're going to have a 10 nanosecond period corresponding to a 100 megahertz clock. Click OK on that constraint. Then we can go to the timing summary for our design, and that identifies the worst negative slack, which effectively implies the amount of headroom that we have above the critical path length till we reach the 10 nanosecond period that's been associated with our design. To understand the critical path length, we also need to factor in the clock uncertainty, because the way the worst negative slack is calculated is by subtracting the sum of the critical path length and the clock uncertainty away from the clock period. That results in the worst negative slack. So for you to work backwards to find the critical path length, you'll need to have a look at the path that has this worst negative slack. Note the paths here are listed in increasing worst negative slack, because the most critical path is the one up the top here, and it has associated with it over here on the right hand side a clock uncertainty of 0.035 nanoseconds. So you'll need that to take that into account in your calculation. You can have a look at the details of this path by clicking on the path. That brings up a window up here which tells us actually that the worst path is the one that arrives on the 6th bit, which is identified by the 5 here of the counter. It tells us here what the data path delay is, what the clock skew is on this particular flip-flop, and the clock uncertainty. Finally, I'd like you to have a look at the utilization of the design. That can be also found under the implemented design. And we see up here, right up the top, that 9 lookup tables, 8 registers, 8 flip-flops, and 11 I/O pins are used in our design. Right. Once you've completed the design and analysed it, you can then implement this counter by embedding it in another top-level design that connects the various components, the enable pin, the clear signal, and the clock to various inputs that are provided by the board, and so that we can also see the contents of the counter. We're going to display the contents on the hexadecimal displays, hex 0 and hex 1, the least significant ones, the ones on the right. So let's have a look at that, that implementation. Programming the board with the design from part 1 for Lab 4 results in a display of 0, 0 corresponding to the register, the counter, not having a value associated with it yet. We have the least significant two switches here, switch 0 and switch 1, which correspond to the asynchronous clear on the basis of, is mapped to switch 0, and the enable signal, the count signal enable, is asserted with switch 1. Since it's an active low clear, we need to assert or deassert the clear by switching it high. And at this point, we can now begin to count by asserting or by pushing down on the central push button here. That corresponds to the clock input for our counter. Since the enable is still low, pressing or depressing that central button has no effect. But when the counter is enabled by switching switch 1 to 1, then from then on we can count on our counter. You'll notice that it's counting hexadecimal, so the least significant 4 bits of the counter are mapped to the least significant 7-segment display here, and the more significant 4 bits are mapped to the next hexadecimal display along, hex 1. You'll probably also notice that the counter sort of jumps very quickly sometimes from one value to the next, but it's actually flashing through all intermediate values here. The reason for that is that this switch bounces, and as it bounces, it re-enables, or it elicits another clock edge for the counter, and therefore the counter counts more than one value seemingly for every press. We'll be addressing the way that you can debounce these push buttons in the next lab. Okay, that's the part 4 demo, or the part 1 demo, sorry, for Lab 4. For part 2 of the lab, you're going to compare the structural design of the 8-bit counter you created in part 1 with a 16-bit counter that you're going to implement using behavioral VHDL. So in this design, you're going to be incrementing the count value in a behavioral description of the counter. Again, I want you to have a look at the structure of the resulting design, and we'll see that in a moment, and to determine the maximum frequency of this design as well as the utilization of the design. I think it'll be quite interesting to compare the findings that you make between this counter and the one that you created for part 1. So let's have a look at what this counter looks like when it's actually implemented. The structure of the 16-bit counter that you're asked to design and implement using a behavioral style code for part 2 of Lab 4 can also be examined by having a look at the RTL schematic. we'll see when this comes up that the structure is actually quite different from what we saw for part 1. Namely, what we have here is a 16-bit register, bits 15 through 0, and they're updated via this adder that adds 1 to the current value of the counter in order to update it when the enable signal is asserted. The worst negative slack, the critical path length, and the utilization can be obtained the same way we obtained them for part 1 for this design. For part 4, you're going to design a couple of counters actually and integrate them into one design. You're going to build a BCD counter that has a clock period or a count period of 1 second. So you want to see, we're going to display a BCD value on the least significant 7-segment display, hex 0, and that counter is going to increment with a period of 1 second. So in order to do this, you're going to use the 100 megahertz free running clock that's provided on the board, and you're going to use that clock to generate a 1 second time signal, which is effectively going to be used as the clock on your BCD counter. To generate a 1 second signal from a 100 megahertz clock, you effectively need to count the appropriate number of clock edges, effectively 100 million of them, and then assert for 1 clock period an output signal that corresponds to the 1 second timer that you need to build this design. That timer is going to be connected to a smaller counter, which is just a BCD counter. Again, that can be described behaviorally, and it's simply going to range in count from 0 to 9 and then back to 0 again. The value of that counter is going to be displayed on the hex 0 component. You're going to create a block diagram that explains how these components are connected together and what sizes the various signals are and what components they're connected to on the Basis 3 board. You're going to implement that design, you're going to download it onto the board, and then you're going to test it. So let's have a look at what that design looks like on the board. Programming part 4 of the lab on the board results in a 1 second BCD counter being displayed on the least significant hex 0 7-segment display. This counter can be cleared at any time by pushing the central push button here, which I'll do now. Clears the counter to 0, which then starts again, counting 1 second per digit through the 10 BCD digits that are available. So I'll just clear that again, and that's it. In Lab 4, there's help available, as there is with the other labs in the course. For this lab, there are project archives with skeleton code available for parts 1, 2, and 4, available from the labs part of the course website. There's the weekly lab sessions. There's 3 different times available during the week for you to get one-on-one help from lab demonstrators during those lab sessions. You're allowed to attend any lab. You're allowed to attend all labs if that's what you wish to do, wherever there is room available. You're allowed to collaborate with your friends, work with your friends, but you have to prepare your own submission. That is, you have to create your own designs. You have to code your designs yourself. You have to implement them and check that they're working properly. For the submission, the submission for this lab involves creating project archives for parts 1, 2, and 4. You'll also need to provide some additional work, the answers to your questions for parts 1 and 2, as well as your block diagram for part 4. That can be captured in a PDF, and the 4 files should then be zipped together and submitted using the Make Submission tab on WebCMS. That's the most reliable way of submitting your work and ensuring that we get to mark it all. The submission for Lab 4 is due by midnight on the 6th of April, which is a Sunday at the end of week 7. So after the week 6 break, you have another week to work on Lab 4. Good luck, and hope you have some fun and learn something.